lean budget design. I'm going to pick up where we left off last time. So I'm going to be talking today about thermal noise, because remember the thermal noise is always a limit of every communication, and we're going to calculate the noise temperature and noise figure of a device. And then proceed towards how do you actually, if you have multiple devices, each one of them coming with a different noise figure or the noise temperature, how do you calculate the noise temperature of the whole system? Now, when it comes to satellite communication, a lot of you are coming from RF propagation, personal communication systems, where we use mostly noise figure, right? And the reason for that is because all of these are terrestrial systems, and we pretty much work at temperature range, which is stays constant, like around 300 kelvins, right? Now, in satellite communication systems, the temperature of the background may vary substantially, and therefore it is much more common to use the equivalent noise temperature of device than to use the noise figure. What I'm going to do today is try to explain the difference between the two and show you how you calculate the noise temperature of first individual devices and then system as a whole. But first, a couple of words about the thermal noise. This is, I guess, noise that is there because there is a motion of the electrons whenever you are not at the 0 Kelvin temperature. And thermal noise is a dominant source of the noise in the microwave portion of the spectrum. A lot of times we call this noise white noise, which implies that it is having the same power spectral density over the entire frequency axis. Of course, this is not possible, right? Because that would make the power of this noise infinite. And in nature, there's very few things that are infinite, right? Whenever we say it's infinite, then it can be infinite in the approximation. So the power spectral density of the thermal noise is derived from the black body radiation. And this is the expression that gives you power spectral density for the noise, one-sided, meaning just for positive frequencies n. H is a Planck's constant, and K is the Boltzmann's constant. You've probably seen them somewhere in your school. So now, if you plot power spectral density of the thermal noise as a function of frequency, as I have done here, where I have the frequency in gigahertz downstairs and power spectral density in milliwatts per hertz upstairs, you end up with a curve that looks like this. Now, how long does it go? It goes up to 1,000 gigahertz. How far is the radio spectrum that we even theoretically when we talk about radio spectrum, we say it's from up to 300 gigahertz, right? So up to here, and you can see that for the entire range of the frequencies that we consider radio spectrum, the power spectral density is constant. As a matter of fact, this shaded area here shows you where the satellite service exists, and you can see that the power spectral density is very much constant, right? And this is the value here. For this plot is given for temperature of 300 kelvins, right? Which gives you this 4 times 10 to the minus 21st watts per hertz, right? There are other sources of noise that exist in satellite communication systems. They're of a different origin. They don't come from thermal motion of the electrons. They come from the various sources here, from the active elements, from discrete nature of the charge, and so on. It turns out most of them are broadband as well. So when you consider the noise in general, you get to think of it as being wideband and mostly white. And that's how we're going to do it in this course. Now, if you look at now some of the quantities here, if you look at that term that was in the exponential, hf over kt, and substitute the values for f and k, kt at 300 kelvins, and you work it out, we can see that this is some small number times frequency in gigahertz. So for all the frequencies, let's say, where we have satellites up to 40 gigahertz, this ratio of HF over KT is very small. And then if something is small, then this minus the exponential can be expressed as 1 plus that, right? So for a small x, you probably know that for the small x, e to the x is approximately 1 plus x plus all x. So when x is small, you can approximate exponential as 1 plus x. So if you do that, then this 1 and 1 cancels, and you know HF over KT. And if you put that back in here, you see that HF and HF cancels, and there's this KT friend that we've seen before. So that's where the KT is coming from, right? There's a first order approximation to the true power spectral density of thermal noise, realizing that for the most frequencies we're way below that frequency where the power spectral density starts decreasing, right? So in all our practical communication applications, we can assume that the power spectral density is flat with a KT, and it only depends on the temperature of what is it that you're looking at, right? In kelvins. Now, so it is white in the spectral domain. Also, it is Gaussian in the amplitude domain. As you know, random processes, we have two forms of descriptions. One is the spectral description, and the other one is the amplitude description. In the spectral, it is flat. It means that across the entire frequency axis, the density is the same. And then in amplitude domain, it exhibits the Gaussian character. Now, what you need to understand here, if you now say it's flat, right, and you say it's flat across the entire frequency axis, then it cannot be Gaussian, right? Why? Because a flat one across the entire axis has an infinite power, right? So that would correspond to a Gaussian with sigma being infinite, right? Really how you should look at it is flat, but under one condition, we always know that we're operating within a certain bandwidth, right? You never say, okay, the noise is from f from 0 to infinity. You say, it's flat and this is my bandwidth. And then when you cut portion of the noise, then you're actually cutting the power of it. And you say, well, what is the power of the noise? Whatever comes in through this front-end filter, and that power becomes this sigma here in this expression. So in the case of the thermal noise, we actually know everything that is there to be known, by just specifying the temperature, because we know it's if I know the temperature, I know its power spectral density, but also if I know the bandwidth that my equivalent bandwidth is, then I know its power, and then I know its Gaussian nature in the amplitude domain. And we're going to be utilizing these expressions throughout this entire course. Now the question that I have here is, what is this BE, the equivalent band, right? And this is sometimes referred to as the noise bandwidth of the system. And the way how it works is, we typically talk about system. We think of a system as being a bandpass, right? So it says this is the frequency range, f minimum to f maximum, right? That I reserve for the operation. But in reality, nothing is this square, right? You usually say my front-end filter has a characteristics that looks somewhat like this, right? So this is, I guess, ideal of frequency response, and this would be real or practical frequency response. And then what would be the equivalent noise bandwidth? The equivalent noise bandwidth would be this one, the bandwidth here, that gives you the same power as the noise through this system, right? So what would be, if we do one-sided calculations, what would be the power of the noise in this case? It would be, or even double-sided. Power of the noise would be integral, let's say f goes from minus infinity to plus infinity, Sn of f, h real of f, magnitude squared, df, right? That's the power of the noise that enters the system, right? You integrate power spectral density times the magnitude square of the front-end filter. Well, you want this to be equal to the B equivalent times the power spectral density KT, right? And then here, since this guy is also, let's say KT over 2 because I'm doing double size. Since this guy is also KT over 2, then they cancel, and you end up with what is the equivalent bandwidth is going to be integral f goes from minus infinity to plus infinity HR of f magnitude squared. Right, so it kind of links this to the actual frequency response. And we can say, for example, that's why a lot of times you say the width of your transponder is, let's say, 40 megahertz, but your equivalent bandwidth is 36 megahertz. Why? Because there's reduction in the noise in these skirts, right? Because so it is equivalent as if you were to have a box that is only 36 megahertz wide. So you reserve 40 kilohertz for this channel, but because that includes the skirts of your filter, your equivalent noise bandwidth is somewhat small for the noise calculation purposes.
If you had like a cascade of filters, then you'd have to get a convolution through all. Right?
Yeah, or just a product in the frequency domain, right?
Yeah.
Just convolution in the time domain, or just a product in the frequency domain of the frequency responses to get the aggregate frequency response. But you will see very soon that really, when it comes to the noise calculations, we'll do quite a few of them. You will see that the noise figure of the whole system and what is important for the noise analysis is determined by the first couple of stages of your receiver. The noise figure of what comes down below is not everything actually after the first LNA, kind of diminishes in importance when it comes to the noise figure. So we'll go through the detailed calculations. Now, let me define here equivalent noise temperature of the device. Now, my background, I guess, professional background is terrestrial, so I tend to say always noise figure, but in satellite we talk more about temperature. So how do we define the temperature? Here's the reality. Let's say you have this scenario. I take a matched source. Remember, everything has to be matched to avoid the reflection of the signal because you're at a very high frequency. So here we're talking about microwave waves and S parameters and those things. So imagine you have your device under consideration and you're looking some source which you, for the sake of this experiment, you put at 0 Kelvin, right? So that means this source causes no noise, right? It's completely noise-free. Why? Because it's at 0 temperature. Now, but this device is not. And what happens as a result of this device being not at the 0 temperature, there will be some noise generated at the output of this device. Now, the noise temperature of the device is the temperature of the resistor that you would need to put at the input of this device to generate the same power as in this case, under assumption that this device is noiseless. So what we're doing is we're saying in reality I have some noise generated inside this device. Well, what should be the equivalent temperature of equivalent matched load here, or source rather, that would give me the same noise power, assuming that no noise is generated in the device itself. This is very similar to what we do with the noise figure. We say, okay, you have a real device that generates some noise at the output. Why does it generate? Because it has, transistors, it has its own resistors, it has all sorts of noise sources throughout the device itself. They all come, and then as a result, you get some noise at the output of the device. Well, when we say the noise temperature of the device, we're actually saying, if this device were to be noise-free, what should be the temperature of the source that I need to put in its input to give me the same kind of noise at the output that I have just coming from this device. Now the question of when you have this kind of mathematical definitions, the question is always how you determine the noise temperature of a given device. And there is something called here Y experiment or Y factor method. Let's say I have a device here under test. Device would always have certain band gain associated with it. Or it can be called system under test, depends whatever it is that you want to test here. It will have its gain, means the power gain from this point to the output. It will have some equivalent noise bandwidth, like given here. And it will have some noise temperature that we need to determine. And the question is how you do that. You hook up the output of the device to the matched power meter, and then you have two sources, one that you cool down as cold as you can get, and the other one that is relatively hot. And then you start writing equations. Let's say when you connect the device under test to a hot device here, the total temperature at the output would be whatever is generated by the device, which would be KT1 times the B, that's the power spectral density, times the gain, right? So that's coming from the device, by the source, right? This is the power of the noise that is being generated by the source, plus the internal noise generated by the device under test. Now, assuming that I'm putting that noise up front, right? So this would have been the power of the noise as seen by this scenario, right? I say there's some power here that comes from the device, and I'm saying, well, that power comes from an equivalent noise source here that goes through the same gain, through the same bandwidth, and contributes to the output. Once you measure this N1, now you switch this, and then you write the same equation for the case where your source is at a different temperature. And then you end up with noise 2 is GKT2 over B plus the internally generated noise. If you divide the two, you can see that most of these things cancel, and then you have T1 plus TE, T2 plus TE is equal N1 and N2, which is your Y factor here. If you carefully examine this equation, it is having only one unknown, which is, you know why, because you measure the powers N1 and N2. You know T1 and T2, you control them at the input. So from this equation, you can easily calculate your equivalent noise temperature of the device as T1 minus YT2 over Y minus 1. The accuracy of this depends on how large can you make this Y, right? Because which means how large can the temperature between these two guys be, and that's under your control. And the larger you make it, the less more stable this denominator down there, so you get the better measurement of the equivalent noise temperature. So there are other methods, but this is one of the methods widely known. And in principle, then using this method, you can determine the noise temperature associated with every device. Through a simple experiment. Now, that's how you determine the noise temperature for devices like amplifiers or filters and so on. Another thing that you have present in all of these systems are your waveguides. And waveguides, they have a physical temperature, but they also, have the losses associated with them. So the question is, how do you determine the equivalent noise temperature of the waveguide? And we just have to carefully go back to the definition of what the noise temperature means and write the equations and then see what comes out. So let's consider a waveguide here. Let's assume that the waveguide is that everything is at the physical temperature T, and that the waveguide introduces losses Ls. So available input noise coming from this source would be KTBN, right? Which is of course T is the temperature, K and Bn is the bandwidth, and K is the constant. The available noise power, the output noise would be KTBN as well. Why? Because everything is at the same temperature, right? So now if you look at how did this noise get here, Well, you can say it is the gain of this guy times K times the temperature of this source plus the gain of this guy times K times the equivalent temperature of this waveguide, and then I assume that there is no noise generated in the waveguide. What I'm actually doing, I'm moving the noise from the waveguide all the way to the front, based on the definition of what is it that how do I define the noise temperature. This is not what happens. This is just fitting my equations. I'm assuming what should be the power of the equivalent source here so that I get the same noise at the output. The noise at the output is this, and now I have two sources. One is the source at the input, which gives me GS KT, and the equivalent source coming from moving the noise generated in the waveguide on the front of the waveguide. Now if you look at this equation and this equation, then you can actually solve for T, and then you end up that the equivalent temperature of the waveguide is 1 over GS, which is the gain of the waveguide, or the number that is smaller than 1, minus 1 times T, or LS minus 1 times T. LS is the loss of the waveguide, the number greater than 1. Now it's important that you realize that this is all in linear, right? So all the gains and losses here are linear quantities. So just to look at it, let's say your waveguide is at the temperature, let's say 300 kelvins, and it has a 3 dB loss. 3 dB loss is 2, so 2 minus 1 gives you 1 times T. So whatever noise you have there, you would actually say that the noise temperature of this waveguide is going to be the T, which means that's an additional source of noise that I need to put at this waveguide input to get my calculations of the noise at the output and the signal to noise ratios. We're going to go back to this. These are concepts. I know I'm explaining them. I hope you get it, at least the basic idea. But don't fool yourself. You have to sit down and kind of carefully think about these things and do quite a few problems before you really get it. You know, it took me a while. I remember when I was learning this for the first time. So from here, you can see that there are two ways for minimizing equivalent noise temperature of the waveguide, and this becomes very important to us. Why? Because you cannot connect antenna directly to the receiver. You have to have something like waveguide that goes from antenna to the receiver. The signal is at its weakest point. Where? Right there, right? Right there after the antenna. And any noise that you have there is impacting the signal in the most significant way. So it's very important that your waveguide has small losses. That first waveguide that connects, and to do that we keep it very short. This is in all like satellite systems that have to be really sensitive. You try to bring in your RF front end as close to the antenna as possible to have your waveguide the shortest, so that you can minimize the loss. And then physical temperature of the waveguide. If you're really trying to detect a weak signal, that is not even uncommon to cool down physically the front end, right? Have a cryogenically cooled front end where you actually run the liquid nitrogen or something to make the temperature of this waveguide really low. And you can see why, because straight from this equation, the temperature equivalent noise temperature of the waveguide is depending on your losses and your physical temperature. If you're able to make losses 0, then this becomes 1 minus 1, so it contributes nothing. Or if you're able to make its temperature 0, then it contributes nothing. It doesn't mean that you're not going to get noise, because some of the noise comes through the antenna, right? Because you're looking at your transmitter, but within the main beam of the antenna, you have other stuff that are coming in. Even if they're not coming through the main beam, they might be coming through the side lobes, or however they get there. Those you cannot do anything about. What you're trying to fight here is make sure that your waveguide does not add additional noise to your signal. Right? So that's as far as the waveguide. So now, let me look at, define the noise figure. Noise figure is related to the noise, equivalent noise temperature. It's slightly, there's a slight twist to it. So let's define the noise figure here and find the relationship between the two. We're not going to be using noise figure a lot in this course, but it's important for you to know the relationship, or at least if you need it, so that you know how to convert between one and the other. Here's the story of the noise figure. You have a noisy network here that has its gain, its bandwidth, and its equivalent temperature, right? And then you have a mesh source that is now at some temperature T0, which we fixed to be 290 kelvins, which is essentially your room temperature, 17 Celsius. So available power at the input, the power that is available here is going to be K T0 times B, right? That's the power that is generated by this source, where T0 is 290 kelvins, this reference temperature here, which for some reason I didn't put 0 here, it should be 0. Now the output temperature, if this network was noise-free, would be just the gain applied to whatever is the power that this source is injecting into this two-port network, right? If the network is noise-free, it would just amplify the noise, right? And whatever comes out is going to be gain G times KT0 times B. Due to sources that are internal to this network, whatever comes at the output would be greater than gain times N input, right? And we can say how much greater? Well, by some factor F. And the factor F is what we call the noise figure. So the actual noise figure is going to be gain times F times KT0 times B. The way how we understand noise figure is this. It is how much I have to multiply the thermal noise that I have at the reference temperature so that I get the same noise power at the output, if I assume that the two-port network is noise-free. So I'm looking at a real system and it has some noise. And if I present how much of I have to multiply the noise at the input to get the same noise if I say that this two-port network is noise-free, right? So that's this guy here. And then if you now do some simple math, you can relate the two. If I just look at what is the noise at the output, I can say that this is KT0 because that's the temperature of the actual source, plus TE, which is the equivalent noise temperature of the two-port network, times the bandwidth times the gain. And it also has to be equal to KT0B times F times the noise figure times the gain. And then by saying, well, the noise has to be the same regardless if I use equivalent temperature or equivalent noise figure for calculations, you get that TE plus T0 is equal F times T0. And then from here, you get the relationship that the equivalent temperature is F minus 1 times T0, and then equivalent noise figure is 1 plus T over T0. This is how you can go back and forth between the two. So the important thing here that you have to understand is this, that I don't know if you've paid attention before, is that along with the noise figure of the receiver comes implicit assumption of the temperature that this receiver is operating. So if we all agree that the receiver is operating at 290, then it makes sense to talk about the noise figure. But if your receiver is not operating at 290, or if the match source at the input is not at 290, then the noise figure cannot be really properly applied here. So the best way is to convert to temperature. In terrestrial communications, what we look at when it comes to the antenna usually has 290 as a temperature. So we are okay there. But if you're pointing satellite antenna, the temperature of what you're looking at may be vastly different. And that's why we like working with the noise the temperature rather than the noise figure in the satellite. Now, in all communication systems, we have a cascaded elements, cascaded subsystems. And the question is, if I have multiple subsystems, what is the equivalent noise temperature or the noise figure of the whole chain? So we're looking here just for the sake of example, two systems. The first one has gain G1, equivalent noise temperature TE1, and F1 is its noise figure, and then the second one comes with its own set of parameters. So if I look at now, what is the objective? Objective is to replace these two with one system with one gain and one equivalent noise figure or the noise temperature. So if I look at now, just walking down this receiver chain, if I calculate the noise at this point, it is going to be gain times KTI, which is the noise temperature of what comes in. But I have to add the equivalent noise temperature of the device itself. So this is the noise that appears at the output of the first device. And that's a result of the noise that is coming into the device plus the noise generated inside the device, right? So this is the output N1. Now if you continue, now this whole thing becomes the noise of what comes in, and you have to add to it the noise generated in the second one. So N output of the second one is going to be gain of the second one times N1 plus gain of the second one times the equivalent noise temperature of the second one. Now if you bring back what N1 is, you end up G1, G2, K, and so on, right? And then if you say, well, let me define G as a product of G1, G2, the total gain of the system from this point to this point, then this equation here becomes G as a common outside, K, Ti plus T1, Te, this should be Te1, right? There's a typo. Do you see that?
No.
It should be Te1. This guy.
I thought it was supposed to be for the entire, this T1.
No, look, N1 is Ti, the one input, plus Te1, the noise temperature of this device, right? So that's this, G1K, Ti plus Te1. So this comes in, right? So this is Te1 times bandwidth, and plus whatever is generated inside this guy. So if you take G, which is G1, G2 as a common gain, then you have Ti plus Te1, this guy, plus Te2, but this one has only G2, right? So it has to be divided by G1, because this G1 is a part of this G, right? And times bandwidth. And then if you look at what is happening here, this becomes Ti, stays the same as the input temperature, and this becomes an equivalent temperature of the whole system. So what's the equivalent temperature of the whole system? Is the temperature of the first one plus the temperature of the second one divided by the gain of the first one, plus the temperature of the third one divided by the product of the gain of the first one and second one, and so on. So if you generalize this to any number of subsystems, then you get the equivalent noise temperature of the chain is going to be the temperature of the first one plus temperature of the second one divided by the gain of the first stage plus the temperature of the second, so third stage divided by the gain of the first two stages, and so on. What you learn here right away is that the most important is the first stage, right? How much of the noise is generated in the first stage, provided that the gain of the first stage is significant, right? So what we have in almost all wireless communication systems, careful design of the front end. There is always what we call LNA, which is an amplifier that is designed not so much to provide a gain, but to provide low noise amplification. And why? Because then the gain of that amplifier figures in all the noise figures and noise temperatures of the devices that come afterwards, and essentially limits the noise figure of the whole system, or noise temperature of the whole system, to whatever is the noise temperature of that element. Now, we had a relationship that we can, using the similar kind of consideration, derive the relationship for the noise figure. And again, you have here that the overall noise figure of the system is the noise figure of the first stage plus the noise figure of the second stage minus 1 divided by the gain of the first stage, and so on. Right? So the moral of the story here is we have to be most careful about the design of the first stage, because that's the one that generates the most noise. That's the most significant from the system's noise temperature. One thing that I want to mention, I can talk about gains, right, which gain is the ratio of the output power to the input power. Gain can be negative in dB, which means these G's can be smaller than 1, right? The gain of 0 dB is linearly 1, right? So that's the device that has no gain, right? Whatever is the power input is the power in the output. If it amplifies the signal, then these G's are greater than 1. And if it attenuates the signal, then it has a gain that is smaller than 1. The gain is always larger than 0 in linear terms, but it can be either positive or negative in logarithmic terms. It's important to remember all the calculations that you see here are done in the linear domain. Right? All these numbers, if you're not given linear noise figures, they would say noise figure is 2 dB, 5 dB, 10 dB. To do these calculations, you have to bring it into linear domain. Okay, and I'll do calculations.
So these were attenuations, then that would destroy your noise figure if you cascade them?
Correct. So if let's say usually here's how it happens. After the waveguide, which is treated separately, I'll show you how you do it. And you have an LNA. LNA has a large gain, but then what you have after LNA is a mixer. Mixer is what brings the signal down to the intermediate frequency where you do all the processing. And the mixer, by its very nature, is non-linear device. If you remember, it multiplies by sinusoidal, so you get energy at double frequency and the lower frequency, and you filter out whatever is a double frequency.
Okay.
So even if it's ideal in a sense that it implements the equations like they were coming from the book, half of the energy is going to be lost. So the mixers have a negative gain in dB, or the gain smaller than 1. The combination that usually appears here is LNA gain times the mixer gain, and you're trying to make sure that this is not huge. Right? So this is large enough so that the noise figure of the mixer does not destroy the overall noise figure of the receiver. Okay. In satellite communications, a lot of times we talk about G to T ratio. They would talk about G to T characteristics of whatever receiver that you're trying to characterize, and you would say this system has a G to T of, let's say, 10 dB, 20 dB, or whatever may be the case. Now, this is kind of an equivalent of the signal-to-noise ratio, right? That we're familiar in a terrestrial world, but because your temperature varies here, that's why we kind of prefer to express it in this way in the satellite communication. So let's define our signal-to-noise ratio, and then isolate GR over TR, and then kind of specify that as a figure of merit for a satellite receiver. Your signal, as it propagates, let's say from the satellite to the ground, is going to be the transmit power, gain of the transmit, gain of the receive antenna divided by the free space power loss. This is what we talked about last time. The noise of the system itself is going to be K times TS times the equivalent band. This is the noise generated inside the system, not the total noise. We'll have to do a separate calculation for the total noise. What is the total noise consisting of? The system noise plus the noise that gets in through the antenna, right? So you have the antenna noise. Let's say you're pointing at the satellite, but there's microwave background radiation that is coming through the main beam there, or your elevation is relatively low, so you're capturing some of the glow from the ground, right? That's the noise that comes in through in with the signal. The TS in this equation here is the equivalent noise temperature of your receiver chain placed at the input, right? This is the noise that you would have to have at the input to generate the same power, assuming that your entire system is noise free. If you now form signal-to-noise ratio, this becomes this equation here, and you can see that the term that isolates at the very end is GR over TS. This is the gain of your receive antenna divided by the overall noise figure of your system. So the rest of it is kind of, it is what it is, right? You are operating at a given transmit power, you have the transmit gain, so this is the given ERP from your transmitter, equivalent bandwidth specified by what is the data rate and what kind of signal you have. Lambda over 4 pi r comes from your free space pop loss. So this is, none of this characterizes the receiver, right? The first characterizes the transmitter, then the waveform, then the distance between, and the only figure of merit that is entirely depending on the receiver is the gain of your antenna divided by the equivalent noise temperature of the system. And it kind of teaches you, okay, I have two knobs that I can turn to control the signal to noise ratio. One is I can increase the gain of my antenna, and we know how to do that, to increase its physical size or do more careful design to improve efficiency of however you do the design of your antenna, or you can work on the decrease of the equivalent noise temperature of your receiver chain by doing careful LNA design, cooling the front end, or whatever are the measures that you deploy. Now, the G over T is, as I said, this is quoted as a figure of merit for a receiver, and it is usually given in dB relative, dB per Kelvin, right? Which is one of those things where if you're in school, you kind of cringe, right? Because if you take GR over T, the units that end up there is, gain is unitless, T is in Kelvin, so it's 1 over Kelvin. And then you take 10 log of that, which you shouldn't be doing, because log only can be defined over a pure number, right? But we do it anyway, and then this dB divided by Kelvin, you don't divide dBs by Kelvin. This whole thing. In other words, if I take, let's say G of T is, let's say, 10 dB per Kelvin, I don't multiply that by 10 Kelvin to get 10 dB, right? That makes no sense. This whole thing is one symbol, right? That explains this process that I just went through, right? You take the ratio of G over T, and you take 10 log of that ratio, even though it's not unitless, but it's okay, right? It's okay, right? So that's so if your gain is relatively small to your temperature, this can be even negative, right? But usually it's a positive number, and the larger it is in dB kelvins, then the better the figure of merit on your satellite receivers. It's one of those things that is kind of, let me see what else. So I have, for the rest of it, let me do a few examples here that kind of illustrate some of these calculations. Some of them are easy examples, some of them will spend some time understanding how they work. So this is a very basic example that I want to move to for a different reason. It says determine the power of thermal noise, so the power of thermal noise and the output of an ideal filter with bandwidth is 100 kilohertz if noise temperature is equal to 300 kelvins. So here's let me give you two methods. The method one is the one that I'm sure you're familiar with. Here's what we have here. you have an ideal filter, and I'm just going to say F without specifying where this is. It may be low pass or band pass. The important thing here is that I should really not call it that this is now power spectral density of the thermal noise, and it's KT one-sided, or it's KT over 2 if it's double-sided. You know that when we do Fourier analysis, we work with a double-sided spectrum that has frequencies going from minus infinity to plus infinity. Then K, power spectral density of the noise is KT over 2. Right? But if you're working one-sided, then you just use that KT. Now, what you know is that if you do, let's say let's just use one-sided for. You're going to say the power of the noise is integral F goes from 0 to plus infinity KT times, since this is ideal filter, I can say pi F over equivalent bandwidth times df, which is essentially giving you KT equivalent. So this is how we do it in communications, or whatever is the subject that we use this calculation. So in other words, here the power of the noise, if I were to do the calculations with the actual number, KT, it's 1.38 times 10 to the minus 23 watts per hertz times what is this constant thing? No, the whole thing is in watt. KT is in watts per hertz. Let me just put in 300, and this whole thing is watts per hertz, and then times 300, times 100 kilohertz, right? Times 100 kilohertz. So that's how you would calculate it. A lot of times, as I said, it's good to remember this number as 4 times 10 to the minus 21 watts per hertz. It's actually slightly larger, but it's negligible difference. And usually you remember this as a whole thing, because KT is the power spectral density of the noise. So when you calculate this, this ends up being 4.14, or 4, close to, let's say, 4 times 10 to the minus 16 watts, which you can translate into minus 154 dBW, or minus 124 dBm. Right? So that's the common way how we've been doing this so far. If you talk to satellite guys, though, here's how they approach this problem. And I'm kind of telling you this because it's not going to matter much in this course, because there's very little you can do that can surprise me. Well, you can do it either way, but when you start, if you start practicing, this is how they would be doing the ring budget. So let me just go through that. First thing that you would find out is they take this KT and then express this in dB watts per hertz. So they would take the 10 log of 4 times 10 to the minus 21 watts per hertz and express this as in a logarithmic units, right? Again, you're taking the log, 10 log of something that's not pure number, right? And this would be, let's say, minus 24 dB watt per hertz, okay? Then they would say, okay, my bandwidth equivalent in dB hertz would be equal 10 log of 100 times 10 to the 5 hertz. And this is 10 to the 5. Oh, what am I doing?
10 to the 3.
10 to the 3, yeah, okay. So the overall thing is 10 to the 5, so it's 50 dB hertz. And then your power in dB watt is going to be your kT in dB watt per hertz plus your equivalent bandwidth in dB hertz. Right? Why plus? Because you're essentially multiplying these two. So this ends up being minus 204 dB watt per hertz plus 50 dB hertz. So this gives you minus 154 watt. And I told you last time, I mean, these are funny things if you're coming from the school background, right? Because first of all, these are different units, and then how do you add, and then this one cancels and all that stuff, right? You actually, to understand what is happening here, you have to go back to what it physically represents. And this is, strictly speaking, incorrect, but with understanding what you're doing, this makes it correct, right? And it's all kind of in an effort to avoid multiplication, right? Which I don't know why are we so scared of multiplication, but I guess that's how a lot of people do it. I'm not gonna insist that you do it this way because it's a degree of confusion. I'm sure if you end up in cell life, they're gonna teach you how to do that in one time. This is good enough for us because this is physics. This is kind of teaching us. But if you want to get ahead and you think that you would like to know how to do it this way, by all means, do it this way. Just make sure that you do enough of examples so that you're confident in your ability to do it without making mistake. Let me do a couple of other problems here. This is example 4.3.1. It says the frequency of operation is 4 gigahertz. We have a 4 gigahertz receiver with following gains and noise temperatures. So you have your antenna. Then let me first draw blocks, and then we'll kind of explain how you convert this into. So this is going to be your RF stage. This is going to be your mixing stage, and this is going to be IM stage. Right? You have the signal coming from antenna. There is an RF stage with your LNA and your front-end amplifier. Then the signal comes with the input frequency of 4 gigahertz. Needs to be brought down to intermediate frequency where it's being processed. So this is done in the mixing stage. And then after that, you have, after you bring the signal down, then the first thing is this IF amplifier, usually the one that has adjustable gain and a relatively large gain, so that you can prepare the signal for either sampling, if you're doing the digital processing, or demodulation, if you're doing analog. Now the RF stage, first of all, there is a temperature here, and we're going to call this one T in. That's the temperature of the background that is being seen, or sometimes it's called T antenna. Right? What is the background radiation of the antenna is looking? Then you have TRF is 50 kelvins, and its gain is 23 dB, right? So 200 times is the gain of the RF stage. Then you have a mixing stage that has a gain of 0 dB and noise temperature of 500 K. And then you have your IF stage that has a gain of 30 dB, 1,000 times, and the noise temperature of 1,000 kelvins, right? So it's very large. And the question is, what is the calculated noise temperature of the system, and then recalculated noise temperature when the mixer has a loss of 10 dB. So this is in case 1. In case 2, we have a mixing of minus 10 dB, which is more realistic. And then the mixer temperature, 500 Kelvin as well. Now the first thing you do is you actually draw this with all the noise taken out of the system. So what I mean by that is say, okay, there's a thing coming in this way. Then the first thing, there's here the noise temperature from this RF stage. And then RF stage is reduced to a pure gain of GRF. Then you have the noise figure of your mixing stage. And then you have the gain of the mixing stage. And then you have the noise temperature of your IF amplifier and the gain of the IF amplifier, right? So that's a great figure. That's the first step. You always kind of draw this figure to know, I mean, exactly what you need to be doing, right? It's one of those things that helps you avoid mistakes, right? Just carefully proceed through steps. Now the next step that you do is all of these gains are typically given in dB. You bring them down to the linear. So GRF is equal to 23 dB, which is 200 linear. G on the mixing stage is 0 dB, which is 1 linear. And then I have GIF, which was 30 dB, which is 1,000 in linear domain. Right? So you have these gains. Now you have everything that allows you to calculate the system noise temperature. So I can say now the TS equivalent is going to be your Tin plus TRF plus T mixing divided by the gain of the RF stage plus T of IF divided by the gain of the RF stage times the gain of the mixing stage. So that's according to that equation. These two guys are coming here. They're coming before any gain. Right? So that's why they're here without a gain, and then every noise temperature that follows is divided by the gain of the previous stage. So in our case, this becomes, what is the T? Do I even say? Tin is 25 Kelvin. So this is 25 Kelvin plus 50 Kelvin plus 500 divided by 200 and plus 1,000 divided by 200 times 1. Right? It's instructive. I didn't do it in my case here, but let me try to do it really quickly here so that you can see. This is 25 plus 50 plus 5 over 2 is 2.5, right? And then 1,000 over 200 is 5. So look at the contribution of the various elements, right? This one, there's nothing we can do about it, right? This one is there. Because that's what comes through the antenna. It's not generated by our system. This is the contribution from RF stage. This is contribution from mixing stage. And this this is contribution from IF stage. Together, they take their, this is 82.5 Kelvin, out of which 50 is due to your front-end RF stage, 25 you could control, only 10, or only 7.5 are due to the internal stages of the front end. If you do the recalculations, that would be part B. So this was part 1. Part 2. Now, gain of the mixing stage is 0.1 minus 10 dB. Then equivalent system noise temperature becomes 25 plus 50 plus 500 divided by 200 and plus 1000 divided by 200 times 0.1. So 200. And this gives you 127.5 Kelvin. Just a simple exercise. So you can see that even the 10 dB reduction in the gain on the mixing stage, didn't do terribly huge change in the noise temperature. Now suppose, I guess, I don't know if I have that, this is maybe I've edited. Suppose you make GRF equal to 50 dB. 50. Then, or this is 10 to the 5. Then if you recalculate the noise temperature, you end up with 75, which is essentially saying.
I don't think it's right. That should be it.
It's right, it's right.
What should it be?
It's right.
Oh, yeah, no problem.
Is it
Right,
right?
it's right, yeah.
It's good that you correct. I do these examples, just like you're doing them now.
Yeah.
So if I punch in good numbers, I get good results. If I mispunch, I get that.
Yeah, correct.
But if you, so that means if you make your RF stage front end with a very high gain, you're essentially the noise figure or the noise temperature of the entire system is dictated by two components. What is it that is coming through the antenna, and how noisy is your LNA?
How practical is it to get a very high gain, low noise amplifier?
That's a very
Because that's like a big trade-off, isn't it?
that's a huge part of the design of your system, and there can be amplifiers that are this good, and then you actually can reduce. Depends what your it depends the cost. Right? Cost is the biggest trade-off here. If you're designing a hub, right, the point where you're having a large throughput, then you can go to the expense and create something like this. But if you're talking about VSATs where you have hundreds or thousands of the small aperture terminals that are giving TV signal to your home or connecting all the Walmarts to the one separate network, then you don't have this. Right? This is very expensive to achieve. But what happens is, you know that very well. This number here, G gain, and essentially the gain of your antenna, noise figure of this guy limits your signal to noise ratio, right? And in a given bandwidth, what that means, if I give you bandwidth and I give you signal to noise ratio limit, that tells you the data rate you can achieve. And data rate is kind of saying, okay, you have this spectrum, this is what you pay for, right? The end customer cares less about any of this, right? All they care is about how many bits per second I'm getting out of this connection. And so this ultimately affects your ability to provide high data. Let me do a couple of more examples here. Four, three, two, from the text. I say, it says consider the system in a previous example with an LNA. So I have GRF of 50 dB. A section of lossy waveguide with attenuation, lossy waveguide with attenuation LS of 2 dB is added in front of element. So now the question is, what is the question? Find the system noise temperature and give the physical temperature of the waveguide. So the physical temperature of this guy is 300 kelvins. And define the noise temperature of find the system noise temperature of, in this case. So here's what we have. We have your Tn. Then you have a lossy waveguide. Its physical temperature is Tp and this Ls. And we already calculated the noise temperature here. or let me just do it as we did initially. So this is your gain of the RF. This is the TRF. Then gain of the temperature of the mixing stage, gain of the mixing stage, and the temperature of the IF stage, and then the gain of the IF stage. Now this one here, we're going to also replace by something that looks like this, right? It will have its gain and it will have its noise temperature. The LS of the waveguide is 2 dB, which means in linear 2 to the 0.1 times 2. Actually, I should say the gain, sorry. Gain of the waveguide is minus 2 dB, which is in linear domain 10 to the minus 0.1 times 2, which gives me 0.631. So that's the gain of the waveguide, right? It's the number smaller than 1. Why? Because it's actually, there's a loss associated with loss is 2 dB, so it's the gain is larger than 1/2, right? But not much larger. Now, what did we say about the equivalent temperature of the waveguide? Is we said that this was LS, LS minus 1 times the physical temperature, which is, I can write this also as 1 over gain minus 1 times the physical temperature. In our case, this becomes 1 over 0.631 minus 1 times 300 Kelvin. And this gives me 175.4. So now, this becomes 100 TES, which is 175.4, and this becomes the gain, which is 0.63. And then from that point, the calculation is the same. Right? Now let's do them. Now you have T. Now, what I have here is, let me just another. I don't know if that's in a notebook. If you do calculations, you can do references at 2 points. This would be the equivalent noise temperature into the waveguide. But it's more common to, even though you have a waveguide, reference everything in front of the LNA. So this would be TS2. So let's calculate both of these noise temperatures. TS1 is the straightforward. We do calculations just like we did so far. So this would be Tn plus T, how do I call it? TS plus TRF divided by the gain S plus T mixing stage times GS times the GRF and plus T of the IF divided by the gain of the waveguide, gain of the RF stage, and gain of the mixing stage. So that's the equivalent temperature. In this case, when you substitute it, this becomes 25 plus 175.4 plus 50 over 0.61 plus, this one was 500 divided by 0.631 times 200, and then plus 1,000 divided by 0.631 times 200 and times 0.1. We're taking the mixing stage to have a gain of minus 10 dB. So when you complete all the calculations, this is 279.8 Kelvin. Right? So that's it, the equivalent noise temperature into the waveguide. If you reference everything at the input to the RF stage, then instead of T in, you have T in plus TES times gain of the waveguide. That's the new T in. That's the temperature of whatever is coming this way. And then plus TRF, and then plus TM over gain of the RF, and plus TIM over gain RF, plus times the gain of the mixing stage. And in our case, this becomes 25 plus 175.4, 0.631 plus 50 plus, this was 500 divided by 200 and plus 1,000 divided by 200 times 0.1. So this gives us the noise temperature 176.6 Kelvin at the input LNA.
The difference is you multiply by the gain of the.
Well, everything is skewed to the, now you say, this whole thing here, I'm not going to know about it. How it's structured, I'm just looking at the temperature of whatever is coming to the left. And you treat the output noise here.
So you wouldn't know what GS is, or you wouldn't know what GS is?
It is here, right?
Yeah.
Because an interesting thing here is, it is not interesting, it's easy to understand that this waveguide attenuates the noise as well that comes through the all right, so do we have time for one more? No. This is the, you have it in your notes, it's the example 431 that talks about just calculating G to T ratio.
Professor, that one's wrong.
Yeah.
Your GRF is
23
dB, not 23.
No, this is 50 dB. Did I mess it up numerically, or did I just?
You use 23. You work with 23 dB.
Oh, so the end is, the result is correct, right? This is 10 to the 5 here. And then it's also 10 to the 5 here and 10 to the 5 in these two places, right? 10 to the 5, 10 to the 5. Okay, so that's it for today.